There's a donut in the wallpaper. No, there's not, you're probably thinking. There's some birds, some flowers, but there's no donut. And yet, there is. In fact, this wallpaper wouldn't be this wallpaper without this donut. In order to see this mythical donut, we're going to need to look at the intersection of a few seemingly unrelated math concepts. And hopefully, by the end of this video, you'll be able to see this donut too. The donut introduces topology. But what is topology? Well, to vastly oversimplify, topology is the study of shapes. But isn't that an oversimplified definition of geometry too? Well, yeah. But while geometry cares more about rigid properties, such as angles and side length, topology cares more about broader properties. A great example to show the distinction between the two is counting edges versus perimeters. Let's look at some 2D shapes made out of Play-Doh. We'll make a triangle, a pentagon, a hexagon, and a square. As I'm sure you could tell, each one of those shapes had a different number of edges, but they all just had the one perimeter. And that's because the perimeter, or really the word we should use is boundary, is a topological element, not a geometric one. So despite all these shapes looking a lot different, they all have the same topology. You can tell this because they were each continuously deformed into each other. Just think of a continuous deformation, like the shapes are made of Play-Doh. You can smush and stretch and do whatever to the Play-Doh you really like, as long as you don't do any violent actions, such as smishing two sides together or tearing it. These are considered illegal actions. But it's not as if these topology police are going to come out of nowhere and arrest you for doing these illegal actions. Just as adding edges and changing the angles of shapes changes the geometry of the shape, doing these illegal actions changes the topology of the shape. And actually, we can start to get a good understanding of all the different types of topological surfaces there are just by messing around and seeing what happens. So let's start breaking the law. But first, let's get some topological technicalities and jargon out of the way. First, we're only looking at surfaces that are two-dimensional and compact, meaning that they're two-dimensional and they have a finite area. Also, we'll have different names for the different topological surfaces. The first surface we looked at, the one we made all the shapes from with Play-Doh, is a surface with boundary, a compact surface with boundary, or a disk. And we're going to use the disk as the starting point to make the rest of our topological surfaces. We left it off as a square, and although that's seemingly arbitrary, it is very much intentional. The square just allows us to do these illegal moves in a way that is neat and clean. Let's start off with something that's pretty simple. Let's glue two opposite sides of the square together. To help better visualize this, we're going to embed the surface into 3 dimensions. Don't worry, this is still very much a 2-dimensional surface, but the stuff we're going to do to it is better visualized in 3. So let's glue those opposite sides together. As we lift up, what happens shouldn't be too surprising. What we get is a cylinder, or more technically an annulus, but we'll stick with cylinder. What you should notice is that the gluing split the one boundary into 2 boundaries, the top and bottom of the cylinder. If you weren't convinced already, this should really affirm that a boundary is a topological element. But it's not the only topological element. Let's see if you can find the rest. Let's do that gluing again. But this time, I made the disk a bit thinner, and I also marked the 2 boundaries that we're going to get after we do the gluing. So we'll go up, but except this time, right before we're about to glue, we're going to give the surface a little half twist. That gives us a surface called a Mobius strip. But wait, the orange side connected to the yellow, and the yellow side connected to the orange. So that means the 2 boundaries that we were going to get are connected, and they're just one big boundary. So if this is just a surface with boundary, what changed topologically? Well, this introduces another topological element that you might have gotten intuition of, but we haven't formally stated yet. The idea is orientability. or sidedness. See, the cylinder has two sides, the inside and the outside. The disk is also two-sided. It has a front and a back, and you can't get from one side to the other without crossing a boundary. But let's look at the Mobius strip. Let's have a two-dimensional creature, we'll call her Ari, live on the Mobius strip, and see what happens as she goes on a little adventure. And it should be noted that to Ari, our little two-dimensional creature, that all this three-dimensional embedding and crazy twisting that's happening to her universe is not something that she can notice. To her, she can just walk in a straight line, like nothing's happened yet. So, as she walks, she walks, she walks, she walks, slow sometimes, faster others, but she gets back to the point where she started. Except this time, she's upside down, or mirror reversed. It's impossible to become mirror reversed on any 2D surface that is orientable. So seeing Ari mirror reversed is proof that the Mobius strip is non-orientable. So cool. We've discovered another topological property, orientability. It's nice that we discovered another property, but it kind of sucks that we have to go to 3 dimensions to visualize what we're even doing. Is there any way to visualize all these gluings that we're doing in just 2 dimensions? Well, yeah, there is. And one of the ways is called a gluing diagram. What we can do is bring back the 2 surfaces and mark where we glue them together with arrows. So now, we can unzip the Mobius strip in the cylinder and put it back in 2 dimensions, with the arrows signifying where we will glue them. Now if you notice, the gluing diagram for the cylinder, the 2 arrows are facing each other. You can draw a line from one head to the other head. However, for the Mobius strip, because we put that half twist in there, the arrows are pointing opposite directions. They're chasing each other. But you can look at these gluing diagrams and realize there's 2 sides that we haven't even touched yet. So we can glue those sides together as well as the sides we're already gluing together. What happens then? Well, first, what are the possibilities for gluing these together? We can glue them like they have facing arrows, or we can glue them like they have chasing arrows. In total, that'll give us 3 options really. 2 pairs of chasing arrows, 2 pairs of facing arrows, or a pair of chasing arrows and a pair of facing arrows. Let's see what happens when we glue those together. First, we'll do the one with 2 pairs of facing arrows. We know what happens when we glue 1 pair of facing arrows together. We get the cylinder. So now, the 2 boundaries that we have on the cylinder, we're going to also glue together. So as we continuously deform this cylinder, we'll start looping it around and then connect the ends. What we'll get is something that looks an awful lot like a donut. See, I promise, we're getting somewhere. Something somewhat notable about the donut, or a torus is its official name, is that it has no boundaries. We glue the 2 boundaries together. But what's arguably even more notable about the torus is that big hole in the middle. We're not going to rigorously define this hole. That's more of a problem for higher dimensions anyway, because you can clearly see the big hole there. But just know that it is our last topological element that we're going to focus on in this video. Next, let's look at the gluing diagram of the surface that has a pair of chasing and a pair of facing arrows. We'll glue the pair of facing arrows together first, like we did last time, and now we'll try to glue the 2 ends together. So let's bend them around, but now we kind of run into a problem. We can't align the 2 arrows neatly like we did last time with the torus. We'd actually need 4 dimensions to properly see this surface, but we don't have 4 dimensions. So we're going to have to do something called a self-intersection. We're going to have to push one end of the surface through the other to properly align them. What we get is a surface called a Klein bottle. But unfortunately for the Klein bottle, it is kind of an awkward middle child between the torus and the next surface we're going to do. So we're not going to focus on it too much on this video. So let's go to that last surface, the one with 2 pairs of chasing arrows. If self-intersection was a problem for the Klein bottle, it's even more so for this surface. It's so much so a problem, in fact, that I'm not even going to try to visualize it in 3 dimensions like I have with the others. We'll just skip right to what it looks like 3-dimensionally. The surface is called the real projected plane. We'll just call it a projected plane for the sake of this video. Just like how for the torus, its only topological feature was that hole it had. For the projected plane, the only really topological feature it has that we care about is the fact that it's non-orientable. There is one last surface that I have left out. It's a surface that has no boundaries, no holes, and is orientable. And it's probably the two-dimensional surface you're really most comfortable with. It's the sphere. Its gluing diagram is shown here. Instead of putting arrows on opposite sides that we match up, we put matching arrows on adjacent sides and just pinch closed. But remember, this is just a sphere topologically, meaning A, it's still two-dimensional, and B, we can smoothly deform it into really any polyhedra that we want, and it'd still be technically a sphere. I know that can get a little confusing, but try to stick with me there. A quick little aside. For the illegal actions, all that we've been doing so far is gluing. There's another illegal action, tearing or ripping, the term we should use is puncturing, that we haven't talked about at all yet. If we puncture stuff instead of glue stuff, will we get topological surfaces that we haven't even touched yet? Well, no. And that's because puncturing is just adding a boundary. Here, let me show you. Let's look at this sphere. What happens if we puncture it? Well, now we have a surface with boundary, because puncturing introduces a boundary. But we already have a name for a surface with a boundary. It's a disk. Well, what happens if we puncture the disk? We're introducing another boundary. Well, what's a surface with two boundaries? A cylinder. And is this topologically equivalent to a cylinder? Yeah. Here's the gluing diagram of it. I think now is a good time to introduce the Euler characteristic. Euler's formula for polyhedra states that for any polyhedra, the number of vertices minus the number of edges plus the number of faces will always equal 2. And this is true for anything that's topologically equivalent, or the word we should use is homeomorphic, to a sphere. But here's a question. Do the other topological surfaces have an Euler characteristic? Is it the same? Is it different? Well, let's look. Remember how a disk is just a punctured sphere? Well, what happens if we puncture this sphere? We can just think that we're removing a face. So if we removed a face, and then we calculate the Euler characteristic, it goes down by 1. So the Euler characteristic for any disk is just 1. I should note that not only does it just remove a face, but it also cuts the vertices and edges around where it punctured the face in half. But this never affects the Euler characteristic, because the number of edges and vertices around a face is always the same. It's kind of hard to prove that, but just take my word on that. And the Euler characteristic ties nicely into another broad concept of mathematics, curvature. If we concentrate all the curvature of the surface onto its vertices and boundaries, then we can measure the angle defect of each vertice and boundary. The angle defect for a vertice is how much the vertice differs from having 360 degrees around it. You have 3 options for this. You can A, have 360 degrees around a vertice, like you have here, so the angle defect would be 0. You could B, have less than 360 degrees around a vertice, so the angle defect for here would be 90, because you need to add 90 degrees around this vertice to get it to 360 degrees, like that one. Or finally, you can have more than 360 degrees around a vertice, like you do here. The angle defect would be negative here. It'd be negative 90, because you would need to remove one of these corners away from the vertice to get it to 360 degrees. Measuring angle defect around boundaries is a bit different. Instead of measuring how much the boundary differs from 360 degrees, we measure how much the boundary differs from 180 degrees. For this part of the boundary, at least this segment of whatever boundary it is, it's perfectly straight. It's 180 degrees. So the angle defect for the boundary would be 0. But if we go over here, this boundary at each corner is missing 90 degrees. So the angle defect would be 90 times the 4 corners, 360. Now, knowing about the angle defect, we can measure the total curvature of a surface just by summing up the angle defect at every vertice or every boundary on the surface. So now let's just look at a one-hole torus. On the outside, it has 8 points of positive curvature that each have positive 90 degrees. But on the inside, it also has 8 points of negative curvature that each have negative 90 degrees. So if you sum that all up, the total curvature of the torus is just 0, because all the curvature cancels out. But what about for a two-hole torus? Well, like the one-hole torus, on the outside, there are 8 points of positive curvature that have a positive 90 degrees around them. But now, there's 16 points of curvature that have negative 90 degrees instead of just 8, meaning there's 8 whole points of negative 90 curvature that's going unaccounted for. If you sum that all up, there's negative 720 degrees of curvature on a 2-hole torus. And remember, in topology, anything that's topologically a 2-hole torus, anything that's homeomorphic to it, will also have the same amount of curvature. So what if we make a 2-hole torus that has a handle now, instead of just lumping them together like that? Well, it'll still have just negative 720 degrees of curvature. Because even though we added 8 new points of positive curvature by adding this handle, we also added 8 new points of negative curvature that all cancel out. So we're back to the 8 points of positive curvature and the 16 points of negative curvature. That's cool and all, but what does it have to do with anything? Well, curvature is actually inherently tied to the Euler characteristic through something called the Gas-Bernet theorem. In it, it states that the curvature of a two-dimensional surface is equal to 2 pi times the Euler characteristic for curvatures in radians. I know I talked in degrees when I talked about the torus and the other shapes, but in general it's written in terms of radians. So just by knowing the total curvature of a torus, which we found to be 0, we now know the Euler number of the torus, which is also 0. Not only that, we know the fact that if we add a torus to anything, as when we connect it to another surface, the Euler number will go down by 2. Before we talk about wallpapers, we should talk about isometries. But what is an isometry? Well, on a plane, an isometry is a distance-preserving transformation. Or, in layman's terms, it's an action you can perform on an object that only changes the position or orientation of the object. There are 4 types of isometries on a plane. Really 5, but 4 that we're going to look at. The first isometry is translation. And it's just moving an object along a line. The second isometry is reflection. You can put a mirror line somewhere on the plane, and it's reflect the object along that mirror line. Straightforward enough. The third isometry is rotation. You can put a rotocenter somewhere on the plane, and then draw a line from the rotocenter to the object you want to rotate. Then, along that rotocenter, acting like a pivot, you rotate the object to really anywhere you want. The fourth isometry is called a glide reflection. For a glide reflection, you put a glide line down. Then, you translate the object parallel to the glide line, and then reflect it across the glide line, based off that translated copy. Now, at first, this kind of just seems like an arbitrary combination of translation and reflection symmetry, but it is in fact its own isometry. Just to clarify, an isometry doesn't move the original object. It makes a copy of the original object, and that's the one that gets moved. Let's also briefly look at symmetries inside of objects, primarily rotational and reflection symmetries inside of objects. Objects with reflection symmetry don't necessarily need to be restrained by just one mirror. While these are important for most of the wallpaper patterns, for the one that we're focusing on, these really aren't. So this is just more for the nice visual than anything. So just sit back and watch. This finally brings us to the crux of this whole video, the orbifold. For orbifolds, instead of imagining all the different symmetries acted upon one object, you can just surround that object with this celestial sphere, we'll call it, and perform the actions upon that. The kicker is, performing the symmetry actions are equivalent to doing all these illegal actions onto the sphere, generating a whole bunch of different topological surfaces. And in order for an object to be able to cover an entire two-dimensional plane, it needs to have zero curvature. In other words, its final orbifold needs to have an Euler number of 0. There are 17 different possible orbifolds that have this property of being able to cover an entire plane. And one of them is simply just turning your sphere into a torus, which, as we all know, has a Euler characteristic of 0. For an object that has an orbifold of a torus, the only symmetry that it has is translational. So John Conway, what I think is one of the cutest math nomenclatures ever, called this a wonder ring. A wonder ring, a wonder ring. Anyway, let's see where the torus is in this wallpaper. So we marked out an area that's the smallest possible area where nothing repeats. And now we're going to move it up and down and left to right to cover the entire plane. But now the bottom side is going to the top side to the bottom side, the right side to the left side, and the left side to the right side, without any twisting or anything like that. So if we wanted to mark it a bit more simply, we could just mark it like this. Hey, look at that. Isn't that funny? There it is. There's the donut. In the wallpaper,